Today I'm going to be talking about PyFR and how we can try and get high order methods to the point where they can be useful and practical in industrial contexts. So I'm going to start with some motivation, and as I'm sure everyone in the audience knows, computational fluid dynamics, or CFD, is the bedrock of several very exciting high-tech industries, from automotive engineering to aerospace engineering to naval architecture, and pretty much everything in between. However, in spite of its considerable success, CFD is not perfect. This is a quote from the NASA CFD Vision 2030 study, where they note that despite its successes, the reliable use of CFD is very much confined to a small but nevertheless important region of the operating design space, and this limitation is due to the inability of current generation methods to reliably predict turbulent separated flows. To kind of better illustrate this, this is a slide I took from Murray Cross at Airbus, which shows the flight envelope for an aircraft. So along the x-axis, we have air equivalent airspeed, and along the y-axis, we have the load on the airframe in G. And everything inside this blue region is where the aircraft needs to be validated. That little red dot centered on the cruise speed is where CFD can be reliably used in a predictive context. The key takeaway being that CFD is really only predictive in a very small region of the operating envelope. And what this typically leads to is over-engineering in the regions where we can't be predictive, and then over-engineering increases costs, it increases weight, and that in turn impacts efficiency. Now, when we're talking about CFD, our ultimate goal, of course, is to solve some form of the Navier-Stokes equations in the vicinity of a complex geometry. And there are many different ways that we can do this with different levels of fidelity. The most expensive approach is a direct numerical simulation, or DNS, where you resolve all of the turbulence scales. These simulations are, of course, very accurate, but also very expensive. At the other end of the spectrum, you have something like a Reynolds average Navier-Stokes simulation, or RANS, that are relatively inexpensive, but also much lower fidelity. And in between the two, you have these intermediate schemes, and in particular, the class of schemes that I'm interested in, which are large eddy simulations, also otherwise known as under-resolved direct numerical simulations, where the goal is to resolve the large-scale structures, but otherwise model the small-scale structures. This modeling either being done explicitly or just left to the numerical scheme. The idea being that we get better fidelity at a much reduced cost compared with the DNS. Hence, when it comes to expanding the envelope of where CFD can be applied, in particular to off-design conditions, my focus is very much on scale-resolving simulations. And on account of this, since you have to simulate small-scale structures, it follows that these simulations are always going to be computationally expensive, even with very good schemes and very efficient implementations thereof. In particular, if you want to do a scale resolving simulation, you firstly need a relatively fine mesh, because you need to be able to resolve these small scale turbulent structures without unwanted dissipation. Secondly, in vortex-dominated flows, you need to be able to track these structures over long distances while keeping dispersion errors under control. In addition, given these simulations are unsteady, what we're fundamentally interested in are turbulent statistics, and collecting these turbulent statistics and getting them to converge often requires hundreds of flow passes over our body or our domain, and that typically translates into millions of explicit time steps. The takeaway from all of this is that the computational cost of a scale resolving simulation can be about 10 million times more expensive than a RAND simulation.
Ah, sì.
As a point of reference, a RAND simulation can be done on a laptop in a couple of minutes. And so multiply that by 10 million, give yourself a supercomputer and a couple of days of compute time, and these simulations start to become viable, but they are nevertheless very expensive. In addition, this expense is often not a favorable kind of expense. What I'm showing on the slide is trends in the capabilities of Intel CPUs from 1994 to the present day. And what we're looking at in green is the bandwidth of the CPU, so how quickly you can get data in and out of memory. And in blue, what we're looking at is the arithmetic capability of the CPU in floating point operations per second. And the key takeaway from this graph is that over the past 30 years, the trend has been that calculations have been getting relatively less expensive than data movement. In the 90s, calculating was expensive, moving data was cheap, and now in 2025, it is the opposite. The key point being that algorithms that seem like a good idea in the mid 1990s are likely not a good idea and not a good fit for modern hardware in 2025. And this is really important because if you want to scale with Moore's law, you need an algorithm that scales according to the blue line rather than the green line. Just to kind of put this into perspective, most CFD codes used for industrial simulations, so around complex geometries, are based around second order accurate finite volume methods. And on modern hardware, you can do a theoretical analysis to show that on a tetrahedral grid, such a code is limited to about 3% of peak flops in the ideal situation, the best possible case. Now, if you could actually implement a code that got 1.5% of peak flops, you'd be doing very, very well indeed. But the theoretical limit for these finite volume schemes is around 3% of peak flops. So clearly, the schemes we have today are not able to make efficient use of the kind of compute resources that we're getting access to. So, what we need are newer schemes. In particular, we need schemes which are geometrically flexible, because if you want to be useful in the context of industrial flows, you need to be able to simulate around complex geometries, and so you need schemes that are geometrically flexible. Secondly, the schemes have to be highly parallel, because computers today, especially GPUs, are extremely parallel. And thirdly, the schemes need to conserve memory bandwidth, because memory bandwidth is the thing that we are not getting more of. Compute is cheap, moving data is expensive, so we want to favor schemes that avoid unnecessary data movement, even if this comes at the cost of extra compute. Within this context, the class of schemes that I would like to pitch to you are the flux reconstruction, or FR, family of schemes. And I'm going to illustrate these schemes by working through how we can solve a simple one-dimensional scalar conservation law using flux reconstruction. So we have our PDE, partial u, partial t, plus partial f, partial x is equal to 0, where f is a flux function, potentially nonlinear, and u is our solution, And our goal is to obtain an approximate solution for U at any point in space and time. So what we're going to do in flux reconstruction, as with many other schemes, is we're going to take our domain and we're going to break it down into elements. These elements need not all be the same size, and I'm going to refer to these elements as omega n. Then, inside each of our elements, we are going to represent the solution as a polynomial of degree k. So I'm showing this in blue here, where this particular illustration is in the case of k is equal to 2. Now, the key thing that you notice here is that my solution is not necessarily continuous across element boundaries. This is a key difference between flux reconstruction and more traditional finite element methods, such as the continuous Galerkin family of schemes that you may be familiar with. So we are similar to most other finite element schemes in the sense our solution is going to be represented by a polynomial inside each element, but where we differ a little bit is that we're going to allow this polynomial to be discontinuous across element boundaries. To proceed, what we need is a means of approximating partial x of f. And more importantly, this approximation needs to sit in the same polynomial space as our solution. In other words, it needs to be a polynomial of degree k. Now, in flux reconstruction, the way that we do this is we form a piecewise continuous approximation of our flux, which is of degree k plus 1. I'm showing this here in orange on the slide. This is going to be 1 degree higher than our solution polynomial. For reasons of computation efficiency, it's beneficial to map each element onto a standard element. The idea being that every element through this mapping then has the same geometry. In our case, after doing this quick transformation, each element will go from -1 to 1. This just makes things easier mathematically and more efficient computationally. And critically means that we just need to focus on what's going on inside of a single element. Then, inside of one of our elements, whose geometry now goes from -1 to 1, we are going to represent the solution using a nodal basis. In other words, we're going to know the solution at a set of points inside of our element, and through this, we can construct a Lagrange-type interpolating polynomial that will be our solution. I'm showing an example of this in the case of k is equal to 2 on the slide. These set of interpolation points are known as solution points, and the number of solution points determines the order of accuracy of our scheme. So in our case, I've used 3 points. That gives me a second order polynomial, and so nominally we expect the scheme to be third order accurate in space. Having constructed our solution polynomial, the obvious thing to do is to evaluate our flux function f of u at each of our solution points. This is easy to do because the flux is just a function of the solution. You know the solution at the solution point. So we can go ahead and evaluate f of u to give us our orange flux polynomial that is of degree k. Next, what we're going to do is take our solution and evaluate that solution polynomial at the element boundaries. So evaluate the polynomial at the location x is equal to -1 and x is equal to 1. This is shown by the blue squares on the slide. we've just taken a polynomial and we've evaluated that polynomial at the boundaries of each element. Then what we have at each of our boundaries is effectively a Riemann problem, because we have a solution from the left-hand side and a solution from the right-hand side. So at the same point in space, we have two different values for the solution. And so by using a Riemann solver, what we can obtain is a flux across that interface. I'm showing this as an orange plus symbol at both of my interfaces. And what this corresponds to is the common flux across that element's boundaries. What flux reconstruction then does, and what makes flux reconstruction unique, is we introduce this idea of a correction function. This is a polynomial of degree k plus 1 that has some very particular properties. Specifically, when evaluated at x is equal to -1, it gives us a value of 1. And when evaluated at x is equal to 1, it gives us a value of 0. The remaining parameters of this polynomial are, to an extent, free, and we'll talk about how we can fix them later on. But for the moment, the two defining properties are its value at x is equal to -1 and its value at x is equal to 1, and it's shown in green on the slide. What we're then going to do is scale this correction function by the size of the jump at the interface. And what I mean by this is the difference between the common interface flux at the left-hand side, that yellow plus, that orange plus symbol, and the value of our flux polynomial evaluated at the boundary. Then we're going to add it into our flux polynomial. The effect being that our flux polynomial will now become of degree k plus 1 and will take on the value of the common interface flux at the left-hand side. This is by definition of how we scaled our correction function by the size of the jump. Then we can mirror that correction function. So it takes on a value of 0 when x is equal to -1 and 1 when x is equal to 1. We can take that correction function. We can scale it by the size of the jump between our common interface flux at the right-hand side and our flux polynomial evaluated at the right-hand side, and add it in. The result of these two corrections is that my flux polynomial inside this element is now of degree k plus 1 and takes on the values of the common interface flux at both the left-hand side and the right-hand side. And if we repeat this for all of the elements in my domain, then what we have is a C0 continuous flux polynomial that is of degree k plus 1 inside each element. With this, we can then take this polynomial and simply differentiate it to give an approximation of partial f partial x that is of degree k. Exactly what we need for the semi-discretized form of my scalar conservation law, which we can then proceed to integrate in time. A neat property of flux reconstruction is that through a suitable choice of correction function, we can recover a whole range of schemes. These include nodal DG schemes, spectral difference schemes, and also some new and novel schemes that don't correspond to any existing high-order method. And this can all be done through tweaking the correction function. This makes flux reconstruction, in some regards, a unifying approach. And I'm showing some examples of different correction functions here on the slide. More importantly, the choice of correction function gives us a means of tuning the dispersion and dissipation relationships of the scheme, and also, in some circumstances, relax the CFL constraint compared with nodal DG. And again, I'm showing an example here on the slide of a dispersion relationship, and you can see that the DG, SD, and G2 schemes have very different dispersion properties. More to the point, everything that I've just presented generalizes extremely nicely into both 2D and 3D, and this isn't just via tensor product type elements, but it also extends very nicely into simplices. Simplices being important, again, if you want to work in the context of complex geometries. So this is a brief overview of flux reconstruction. Now let's look at PyFR, which is an implementation of the flux reconstruction approach that's predominantly written quite novelly in the Python programming language. Here, I'm outlining some of the major features of PyFR. It supports compressible and incompressible Euler and Navier-Stokes, arbitrary order FR on all of the usual element types in 2D and 3D. We have all the time-stepping schemes you would expect, a whole host of stabilization techniques, including anti-aliasing, modal filtering, and entropy filtering. We have a few shock capturing techniques, which are important in compressible flows. We are able to run on a variety of different platforms, including CPU clusters, AMD GPUs, Apple GPUs, Intel GPUs, and NVIDIA GPUs, and clusters thereof. And we have a variety of plugins that provide us with additional physics capabilities. These include things like turbulence generation, in situ visualization, time averaging, and Fox-Williams-Hawkins aeroacoustic analogy for solving acoustic problems. So there is a lot of functionality and some quite unique bits of functionality, at least in the context of high order schemes, especially when it comes to things like turbulent inflows and shock capturing. The high-level structure of the code is quite interesting. It has an outer layer, which is very much written in Python and is completely hardware independent. And this handles things like problem setup, scheduling kernels, and distributed memory parallelism. And then when you get down to flux reconstruction itself, you find that operations typically take the form of either matrix multiplications, which are used to represent data interpolation and extrapolation operations, and pointwise nonlinear kernels that encode things such as your flux function and your Riemann solver. For the matrix multiplication kernels, you can usually just pass them off to a vendor-provided linear algebra library, although we do have a few of our own libraries that we've written to specialize certain cases. These are libxsmm and gimmick, but fundamentally they're just slightly smarter ways of doing very specific types of matrix multiplication. And then for the pointwise nonlinear kernels, what we do is we have our own domain-specific language that we use to express the kernels in. And then at runtime, these kernels are translated into either C code, CUDA code, HIP code, OpenCL code, or Metal code. That code is then compiled, linked, and loaded at runtime. So all of this happens when PyFR starts up. All of these kernels are generated and compiled on the fly. And then it's these kernels which the Python outer layer invokes. So all of the heavyweight calculations are always done by highly optimized code, never in Python, but this code is generated dynamically on the fly. And we have quite a few other tricks up our sleeve in terms of our implementation. In particular, we use a task graph structure internally to represent the various operations that are needed and the dependencies between operations. I'm showing an example of a task graph here on the right-hand side. And beyond this, we also make extensive use of runtime code generation with auto-tuning. So we'll often generate several kernels at startup, we'll benchmark to see which one works best for your problem, and we'll proceed with that. This again just helps with performance portability and getting the best possible performance out of the code with minimal user intervention. And what this enables is heterogeneous computing from a homogeneous code base. So we can run on everything from a Raspberry Pi to a standard laptop to a high-end workstation to a top 500 supercomputer, all from fundamentally the same code base with exactly the same functionality in all cases. Just to give you a flavor of what this domain-specific language is, because it is quite an unusual feature, what I'm showing here on the left-hand side of the slide is an inviscid flux operation. So if you look closely, you can see bits where we compute velocities, we compute the pressure, and then we compute the momentum fluxes. This is a kernel that's been specified in PyFR's domain-specific language. And I just want to show the process by which it gets translated into pseudocode on the right-hand side. Firstly, you'll note that the code is very messy and the indexing is quite disgusting. This is all done for performance reasons, but again, it's something that the domain-specific language completely abstracts. So firstly, it abstracts away data layout. You can see on the left, we're just accessing what we think is the zeroth component of an array. But on the right, it expands out to this quite unpleasant expression. This is and better cache locality by using very fancy data structures, and the domain-specific language can hide the specifics of these structures. Secondly, the kernels can be templated based off of runtime parameters. So you can see here on the left, we have ndims encased between brackets, and then that gets substituted for the value 2 in the kernel. Ndims here being the number of spatial dimensions in your simulation. So this lets us write a kernel once that is very generic, but have it get translated into highly optimized code with no overhead at runtime. This idea extends in that we can also use Python to generate our code. So on the left-hand side here, we have a Python for loop. And on the right-hand side, that generates 4 lines of actual code. So this again lets us have a single template that works for 2D and 3D and guarantee that there's no overhead at runtime. To give you an idea of where performance lands, I'm going to consider a tetrahedral grid with degree 7 solution polynomials and explicit Navier-Stokes. We're going to have a reasonably big mesh with 12 times 105 cubed elements, and we're going to compare Frontier, which has AMD MI250X GPUs, and Alps, which has NVIDIA GH200 GPUs. Our metric for measuring performance is in gigadofs per second, and the way you interpret this number is if you have a simulation with 10 to the 9 DOFs, and you conclude that it takes 100,000 RK4 time steps to collect good statistics, then if you know the performance of your code in gigadofs per second, you can easily get the runtime in seconds just by figuring out how many right-hand side evaluations you need to do, multiplying it by the number of degrees of freedom you have in your simulation, and then dividing by the performance of your code in gigadofs per second. So on Frontier, we're going to start on 16 ranks, which for bizarre reasons corresponds to 8 GPUs because there are 2 dies on each GPU that come up as their own rank. And our baseline performance on 16 ranks is about 26 gigadofs per second. And then we're going to strong scale this problem out. And that strong scaling is shown by the blue line. And you can see that going up to about 512 ranks, we still get very respectable scaling at about 80% of peak parallel efficiency. And we continue scaling all the way to 2048, although by then things have started to drop off a bit. But this is still very good baseline performance at 26 gigadofs per second on 16 ranks, and good scaling up to 512 ranks. If we go to ALPS, which is an NVIDIA system, we see that 16 ranks there gets us 96 gigadofs per second, which, if you'll note, is quite a bit higher than on Frontier. This is because the GPUs themselves are somewhat more capable. And in addition, the strong scaling is substantially improved to the point where we're almost at 80% parallel efficiency when scaling from 16 ranks to 1,024 ranks. Again, strong scaling being extremely important because we're fundamentally interested in time to solution. And so being able to scale your code out further means you can bring that time to solution down, which is extremely relevant for industrial cases. Next, I would like to talk about some of our more recent work around implicit time stepping. So everything I've shown you so far has been in the context of explicit time stepping. And I would argue that, contrary to common wisdom, explicit time stepping is viable even for simulations with Reynolds numbers in the millions. And actually going a bit further, we've recently been employing explicit time stepping in the context of reacting flow simulations with finite rate chemistry and haven't had what we would call any major issues. So this idea that you have to be implicit to solve real world problems doesn't hold up to scrutiny. Hence, our motivation for considering implicit time stepping and why we're interested in implicit time stepping is somewhat non-traditional. Firstly, we want to be able to run on lower quality grids. So with explicit time stepping, one small element in your grid can ruin your day. This is something we would like to get away from. The idea being that we trade extensive manual labor in the meshing process for inexpensive compute time in the solver. And this is vital for industrial adoption, where low quality grids are very much the norm. In academia, we can have students sit down for a couple of weeks to make a grid, but that simply doesn't fly in industry. Secondly, we want to expose more parallelism. So as I think I mentioned, I'm very interested in strong scaling. And one of the things that implicit promises is the ability to scale out further. That is to say, you can saturate your hardware with a smaller number of elements, and that means you can scale out further, and so potentially get a reduced time to solution. Now, implicit time stepping is very difficult within the context of high-order methods. And practically speaking, if you want something that works well in parallel, your only option is to do the standard Jacobian-free Newton-Krylov type approach with block Jacobi preconditioning. This is the only approach that exposes the kind of parallelism you need to work well on a GPU. Things like ILU and algebraic multigrid really just don't hold up with the extreme amounts of parallelism that you see on modern hardware. However, even with a preconditioner as simple as block Jacobi, Each block, so you do one block per element in your simulation, has a size which scales as the polynomial order cubed. And what this means is that even for a hexahedral element at a relatively modest polynomial order, you're looking at a Jacobian matrix for that element, which is coming in at around 3 megabytes in size. And that's just for one element, and every element has their own matrix. So this is bad both in terms of its memory requirements and its memory bandwidth requirements. But with this, I will make a claim that most of the stiffness that we experience in our simulations is geometric in nature and has only a weak dependency on the solution. And to try and illustrate what I mean here, we're going to look at a classic case, which is a Taylor-Green vortex at Reynolds number 1600. And what we're going to do is use a structured hexahedral grid with degree 3 polynomials for a total of 64 cubed degrees of freedom, and we're going to run for 20 convective times. So this is roughly what the simulation looks like. If you haven't seen a Taylor-Green vortex before, you start with large-scale coherent structures, the simulation runs, viscosity does its thing, those vortices begin to break down into ever smaller and smaller structures until eventually it just becomes a homogeneous soup. Now, what we're going to do here is try and solve this Taylor-Green vortex problem implicitly using block Jacobi preconditioning. But what we're going to do is compute our element local Jacobians once at t is 0, and we're going to freeze these Jacobians indefinitely. So the Jacobians that are being used for our preconditioning are going to be frozen throughout the entire simulation. And what we're going to compare against is explicit time stepping with adaptive RK45 and the trapezium rule with straight GM-res without any kind of preconditioner. And what you can see here, looking at this plot, which shows entropy as a function of time, is that there is essentially no real difference between explicit GM-res but with no preconditioner and GM-res with our frozen block Jacobi preconditioner. And again, this might be quite surprising because the physics of the simulation changes quite drastically from the initial condition to what's going on around t is 9 to the final condition around t is 20. Yet we're sticking with the same preconditioning matrix from t is equal to 0. To give you an idea of where things land, unsurprisingly for this problem, explicit is the most efficient, followed by the trapezium rule with straight GM-res, and followed after that by the trapezium rule with block Jacobi. However, implicit, as you might expect, does get you a bigger time step, and we can also see that by using a preconditioner for GM-res, we can drop down from 4 Newton iterations on average down to just 1 Newton iteration on average per implicit time step, with the number of GM-res iterations being limited in all cases to 5. To give you an idea of how the performance breaks down, you can see that the majority of our time is spent in the application of the preconditioner and followed by other, which includes your right-hand side evaluations and the Arnoldi iterations needed for GM-res. The Jacobian inversion, because again, your preconditioner is an inverse Jacobian, doesn't take up much time at all. even though you're inverting relatively large matrices, as this can all be perfectly offloaded to the GPU. Now here, an obvious improvement is to simply store your inverse Jacobian preconditioning matrices in single position. So this means you need half the memory and half the bandwidth. Importantly though, all the calculations are still done double precision. It is just the entries of the preconditioner matrix which are stored single precision and then casted to double precision. This has no appreciable impact on convergence, but greatly improves performance, as you can see in the plot to the right, where the amount of preconditioning time is reduced substantially. It's not quite half, but it's not far off. Looking at a more challenging case, let's look at an SD7003 aerofoil at Reynolds number 60,000, an effectively incompressible Mach number of 0.2 and an 8-degree angle of attack. We're going to use degree 4 solution polynomials with about 140,000 hexahedral elements, and we're going to run for 5 convective time units over our airfoil. So here, I'm just showing some ISO services of Q criterion to give you an idea of what the flow looks like. And here is where the performance lands. As expected, the implicit schemes, both unpreconditioned, preconditioned, and preconditioned with a single precision inverse, all allow you to take somewhat larger time steps than explicit, and that the best overall performance comes from straight GM-res in this particular case. So unpreconditioned GM-res with the trapezium rule. This is then closely followed by the explicit scheme and then block Jacobi with single precision preconditioning. But let's make things more interesting and consider messing up the grid. By this, I mean we are going to deliberately shrink one layer of elements in my grid. So these elements are about 8 times smaller than they were before. The idea being that we want to replicate a real-world low-quality grid. So we are going to deliberately make some of our elements obnoxiously small and then see what happens to performance. And here, the story is very different. You can see that explicit is now much, much slower, and it needs a substantially decreased time step. The implicit trapezium rule with straight GM-res now needs several more Newton iterations to converge, but the amount of extra work required by the block Jacobi preconditioned approach is only slightly more than before. In other words, this is showing much better scaling as elements are shrunk than explicit and straight GM-res, to the point where now the implicit trapezium rule with single precision block Jacobians is the most efficient. Indeed, while explicit time stepping got about a factor of 5 slower, GM-res got about a factor of 3.4 slower, the block Jacobi preconditioning only got about 1.4 times slower. And this really does show the benefits of preconditioned implicit within the context of poor quality grids. It's not as nice a scaling as you might see with ILU or algebraic multigrid, but neither of these approaches are practical within a highly parallel setting, and so it isn't really suitable to compare against them. And indeed, you don't expect block Jacobi to deliver invariant behavior with element size. Taking things further, though, while freezing Jacobians and reducing their precision is good, further improvements are necessary for this to become practical. And so the current research on my group is clustering Jacobians so that several different elements on a rank all share the same preconditioning matrix. In effect, your preconditioning operation goes from a matrix vector product to a matrix-matrix multiplication, and so you save both memory and memory bandwidth. I'm going to show a preliminary example of this for the Taylor-Green vortex, since in that case, as it's a nice structured grid, all elements have exactly the same shape. And so what we're going to do is give every single element in that domain the same preconditioning matrix. And here you can see the overall performance profile, where we're now doing single precision block Jacobi preconditioning, but where all of my elements share the same preconditioning matrix, and performance is substantially improved still. This allowing for greatly reduced costs, although it should be said that actually writing the kernels to perform these preconditioning operations is somewhat more fiddly, and doing this well is an ongoing area of research. So, in summary, I've presented PyFR, which is a cross-platform tool geared towards unsteady flow simulations. It's been developed and tested at scale. And I've also showcased some novel approaches for high-order implicit time stepping, which is suitable for GPUs.